I'm Mr. McBrien. This is SCH4U Catalysis. So a catalyst we've already discussed a little bit. What we want to do today is go into a bit more detail, go through a few more examples to illustrate the basic principles of catalysis, and get us essentially a feel for what a catalyst does in a reaction. So what is a catalyst? A catalyst is a substance that changes the rate of a reaction, almost always increasing that rate, without being consumed. So if we take the simple example of the decomposition of peroxide in aqueous solution to form liquid water and oxygen, this is generally a pretty slow process. We can have a bottle of hydrogen peroxide under the counter in the kitchen, and it'll last a fair amount of time before it decomposes into these simple products. Now, in contrast, if we add a small amount of manganese dioxide, this exact same process, this same reaction of 2 molecules of hydrogen peroxide going to 2 water molecules and a molecule of oxygen. If manganese dioxide is present in a small amount, this reaction is extremely fast, on a scale of seconds rather than on a scale of years. If you want to have a look at this reaction, there's plenty of online videos. There's a hyperlink in the slides here to have a look at a video of this reaction. It is quite dramatic. So catalysts can speed up reactions considerably. We generally group catalysts into 2 groups. Heterogeneous catalysts, very common ones, where the catalyst is in a different phase, a different state than the reactants. For example, we can have a solid catalyst like manganese dioxide catalyzing a liquid phase reaction like aqueous hydrogen peroxide. We can also have homogeneous catalysts. These catalysts will be in the same phase as the reactants. For example, a gas phase catalyst catalyzing a gas phase reaction. There are lots of important heterogeneous catalysts. Iron oxide is a catalyst for the famous Haber process, in which nitrogen gas and hydrogen gas are reacted to form ammonia gas. Nickel can catalyze hydrogenation of food oils, so taking plant oils, reacting them with hydrogen gas to form margarine. And maybe the most common artificial process, platinum catalysts in catalytic converters convert 2 very toxic gases, carbon monoxide and nitrogen dioxide. In both cases, platinum can catalyze a reaction to make much more innocuous gases. So carbon monoxide can be reacted with oxygen to give carbon dioxide, and nitrogen dioxide will spontaneously decompose into nitrogen gas and 2 oxygen molecules. All 3 of these components are natural components of our atmosphere. So we can take very toxic stuff that would be coming out of the tailpipe of an automobile and turn it into normal components of the atmosphere. So if you've ever been driving behind an older vehicle, all of those horrific smells that are coming out of it are probably due to the fact that the catalytic converter is missing or has been damaged in some way. So how do these catalysts work? Essentially, they act to change the reaction mechanism and thus lower the activation energy for a reaction. So let's take this graphic here, and our first curve up top is our uncatalyzed reaction. The activated complex requires a great deal of energy to be put in before that complex can be generated. So this is the minimum energy of our collisions that's required for the uncatalyzed reaction. And that's a great deal of energy, and thus the number of collisions that can be achieved at normal temperatures is fairly low. Now, in contrast, our catalyzed reaction has a different activated complex. Remember, the mechanism has changed, and has a lower activation energy. And for this reason, there's much less energy that needs to be put in, and far more collisions will result in an effective reaction to generate our products. So while our potential energy has to go much higher, one thing that's very important to realize is that in both cases, the change in energy, the enthalpy change between reactants and products, is the same. So this means even though the reaction has taken a different path, the reactants and products remain the same, and the energy we get out is the same. And this is a very important concept. So let's sum up some of the things that we just covered. The catalyst changes the reaction mechanism, but doesn't change the net reaction. The activation energy for the catalyzed reaction is less, and this is because of the change in the activated complex. Now, one of the things of which we need to be aware is that when the reaction is completed, when the products have been generated, the catalyst will have been regenerated. This means it's not consumed or permanently changed in any way. As we've mentioned, the reactants and products are the same whether it's a catalyzed or uncatalyzed reaction. And for this reason, the enthalpy of reaction is also unchanged. Now, it should be obvious that the amount of products obtained will be the same as well. The only change in the reaction is that it will occur more quickly. Okay, so let's talk about some homogeneous catalysts. So remember, homogeneous catalysts are in the same phase as the reactants. Now, one of the most important is the destruction of ozone. So throughout the 60s, 70s, and 80s, chlorinated chlorofluorocarbons were used as propellants in aerosol cans. And the Montreal Protocol eventually discontinued their use. But during the 30 or so years that they were used, unfortunately, they caused a massive destruction in the ozone layer that protects us from UV light. So how did they do this? Well, in fact, they reacted with the UV light to produce free radicals. So in this case, we've got our simple molecule based on methane, and it's bumping off a chlorine, what we call a free radical, with an unpaired electron. So the UV light generates two free radicals, one of which reacts readily with ozone. And this forms this other free radical molecule and an oxygen molecule. Doesn't seem too bad, except for the fact that this free radical reacts with another ozone molecule to generate two more oxygen molecules, and regenerates our chlorine-free radical. Now, if we do some quick cancellation here, we can see that our free radicals all cancel out, and our net reaction is 2 ozone molecules generating 3 oxygen molecules. And because all of these free radicals cancel out, they can move on to continue generating more and more oxygen from ozone. The process by which they eventually are destroyed is something different and beyond the scope of this discussion. The important thing to realize here is just a few molecules of chlorofluorocarbons can cause the destruction of a large number of molecules of ozone. So, and this occurs by the same kind of process we've discussed previously. The reaction of ozone with an oxygen radical is in an uncatalyzed reaction has a very high activation energy, is not likely to occur even in the high energy environment of the atmosphere. And so this reaction is, while significant, slow enough to mean that we have a stable ozone layer in the atmosphere. In contrast, the addition of chlorine radicals drops this activation energy considerably and speeds that reaction. Notice that our reaction pathway still describes this situation of the chlorine radical being involved in the reaction as one of the reactants on the left, but regenerated on the right such that it's not consumed. Now, another catalyst that is important is simply representative of a class. Inside virtually every living creature, there are very large numbers of catalysts that govern the reactions that occur inside their bodies and inside their cells. For example, catalase breaks down hydrogen peroxide, which is produced as a result of some metabolic processes. Now, peroxide is a pretty damaging compound, causing cancer and all kinds of other aging processes and other things. So it's important for our bodies to get rid of hydrogen peroxide as quickly as possible. And again, we've already talked about how slow this reaction is without a catalysis occurring. Well, the good news is we have enzymes that perform the same process as manganese dioxide, helping to speed the breakdown of damaging hydrogen peroxide into innocuous liquid water and oxygen. And so catalysts, you may be tempted to think of them as being very small molecules, like solid nickel or solid platinum, or simple chlorofluorocarbons. While in fact, in this case, this is a macromolecule with a molecular mass of about 240,000. So to summarize, catalysts change the rate of reaction without being consumed in that reaction. The change in the reaction rate is a result in the change of the reaction mechanism, not the equation, not the overall reaction itself. And catalysts are extremely important in artificial processes, in biological processes, and in environmental reactions as well. For your homework, please review the notes. There's some additional information there. And have a look at the overall reactions worksheet. It wraps up a lot of the concepts of this unit, so it'll be a good idea to go through it in a fair amount of detail. If you want to do some more reading on the ozone layer, there's a pretty good recent reference in this Forbes article here. Thank you very much, and have a great night.